So in this video we look at an example of finding the extreme values of a function using the second derivative test. And so if you're asked to find the extreme values, basically the local maximums and local minimums of a function, local maximums and minimums, what we're trying to do here then is to split this problem into two steps. And the first step is to essentially find the critical values. And out of all possible values of x and y, it's the critical values which are the only places where you have a chance to have a local maximum or minimum. To determine to determine the type of extrema, we're going to run the second derivative test at that critical value, which means that you first need to find fxx. You need to determine the discriminant d, which is equal to fxx fyy minus fxy squared. That is the discriminant d. And you need to determine the signs of those, plus or minus, positive or negative. And depending on the signs of fxx and the discriminant d, that will determine whether or not you have a local maximum or a local minimum. Okay, so in this example, we're going to just focus on one particular function. Okay, and that function is z is equal to 4 plus 3x plus x squared minus 3y plus xy plus y squared. And evidently that I'm going to leave it up to you to take the gradient and set it equal to 0. And when you do that, you get a value x is equal to -3, y is equal to -3. So basically what we're saying is that at the point P, -3, +3, that the gradient at that point is equal to the 0 vector. And what that is going to say is that then any direction u that you pick, for example, maybe you pick the direction 1, 0, the x direction. If you were to find the derivative of the function in that direction at that point, you would get the gradient of the function at p dotted with the direction vector 1, 0. And because the gradient is 0, no matter what direction you pick, you will get 0 for the directional derivative. And that is what we're seeing here, that if we look at a curve on the surface, the tangent line to the curve on the surface through this point, p is equal to -3, 3, is flat in that direction. Okay, so essentially what we have is a function, right? Z is equal to f of xy. We found that at a particular point P, a critical point in this case, that no matter what direction you pick, no matter what direction you pick, the function is going to be flat in that direction. What we don't know is the function flat because it's curving downward, or is it because the function is curving upward? Or is it flat because you're at a nice convenient point where there is a saddle point? So it's flat just at that one point. Flat this way and flat that way. So this is why we need to finish the second derivative test. But step one is to find the critical values, which we have done. Okay, let's move on to the next step now. Okay. So what we can see here is that we've got the gradient, and we now have the Hessian. So the Hessian of the function at the point P turns out to be this matrix here, 2, 1, 1, 2. Okay? And to get a sense of what's going on with this function, the Hessian of the function at the point P, sorry, I've written that terribly. So if you take any direction, let's say take the direction 1, 0, and you have the Hessian at that point is 2, 1, 1, 2. When you compute the second directional derivative, you get 2, 1, 1, 2. And now here's something interesting to note. When you do this second directional derivative and you multiply this out, you'll get 2, 1, dot product with 1, 0 is 2, 1, 2 dotted with 1, 0 is 1, and then 1, 0 dotted with 2, 1 is equal to 2. So when you dot product the Hessian with the x direction, the answer you end up getting is 2, and it is particularly that number 2 right there. It is the second partial derivative of the function. Okay. So what we're trying to do here is we've got a sense that this function in one particular direction looks like it is a positive number. So in one particular direction, the function is curving upward. How about all the other possible directions? Well, that's where the second derivative test came in. Okay, all we need to do here is the function in that one particular direction pointing upward. Right? What about all the other directions? Right? What about any other direction you try? Is the function pointing upward in those directions also? Okay. In which case would the function look like a paraboloid facing upward? And that's what the second derivative test is meant to do for you. The second derivative test will say when was the Hessian in any direction? Did that come out to be positive or negative or 0 or something else, right? So the key here was to look at fxx at the point P, which this point P is a critical value. And here we can see from the Hessian that fxx is equal to 2, which is a positive number. D is the determinant of the Hessian, okay? And that will be 2 times 2 minus 1 times 1, which is called fxx, fyy minus fxy squared. Right? So that gives you 4 minus 1, which is equal to 3, which is also a positive number. So once fxx and d came out to be positive, we knew that that was enough to determine that the second derivative in any direction was positive, and therefore we know that the function is going to look like a quadratic approximation that is opening upward in all possible directions. Okay? And we can test that out with a picture. Here's what we end up seeing. That function at that particular critical point does look like a bowl shape opening upward, and its quadratic approximation would look like a paraboloid. Right? Now the quadratic approximation is not an exact graph of what the function looks like, but it's an approximation near the critical value. Okay? So we have determined that the one critical point in this case, at that one critical point, there is a local minimum of this function. Okay? And that is the first example of the second derivative test for the extreme values of a function of two variables.